I am Jun Li from China University of Mining and Technology at Beijing. And I'm really honored to be the host of this talk. Today, we are very happy to invite Dr. Wanyun Shao to give a talk about her recent research. Dr. Shao is currently an assistant professor of geography at the University of Alabama. She is a research fellow for the National Science Foundation in labeling next generation of hazards and disaster research fellowship program for the 2019 to 2021. She was an early career research fellow of the National Science Academy of Sciences, Engineering, and Medicine Gulf Research Program. Her primary research interests are focused on human-environment interactions at various geographic scales and their policy implications. Dr. Shao's major publications have appeared in numerous reputable international journals, including Annals of AAG, Water Research, etc. Now, let's welcome Dr. Shao, please.
Good evening, everyone. Good morning and good afternoon. Thank you for coming to my talk. Can everybody see my screen? Which side? Let me see if I can. So
yes, we can see.
Can you see the whole screen or just?
No, right now it's not full screen. I think you need to switch your screen.
Okay, let me do a quick switch. Sorry about the.
It's okay.
Should be this one. Can you see the whole screen now?
Yes.
Okay, here we go. So once again, good evening, good morning, and good afternoon. My name is Wanyun Shao. I'm a faculty member at the Department of Geography at the University of Alabama. So today I'm going to continue the topic on community resilience. Last week, Dr. Chang gave us a wonderful presentation on his research. So from his talk, we learned that despite the intense research on resilience, there is still a lack of consensus on how to define resilience, let alone how to measure resilience. So in today's talk, I'm going to introduce you to my own research. In my research, I would argue that behavioral dimension, specifically risk decision-making, is a critical component that can contribute to resilience. So without further ado, let's dive in. Okay, can you, for some reason, can you see the next? Okay, here we go. So here is a bare bone framework I laid out. So at the core is resilience. And my contention is that resilience is the outcome of interactions between hazards, vulnerability, and risk decision-making. So to make it more specific, I created there's some, okay, I'm so sorry about the technical issues today. So to make it more specific, I expanded the bare bones structure. So here is another conceptual framework I have composed. Once again, at the core is the community resilience. Hazards, vulnerability, and disaster on the left side, and risk mitigation on the right side, altogether contribute to community resilience. And all these are connected, whether they are at the aggregate level or at the individual level. Here is what I would call the cycle of disaster. We know that disaster is the outcome of the interaction between hazards and vulnerability. So every time when a disaster occurs, people will develop a heightened risk perception, and a heightened risk perception will lead to risk mitigation measures, behaviors. For instance, every time when a major flood occurs, people whose houses have been flooded naturally develop high level of risk perception of flooding for the future. And that heightened risk perception leads them to adopt a series of risk mitigation measures, such as buying flood insurance, elevating their houses, applying flood-proofing material around their houses. And over time, their risk mitigation measures will lead to reduced risk perception because they feel they are secure. And that sense of security can lead to, over a long run, can lead to complacency. And also, a lot of research has informed us over time, risk awareness and risk perception and alertness will decay over time. So altogether, those factors will lead to behavioral change. That complacency will lead people not paying enough attention to those risks. And behavioral change will increase their exposure to hazards. Therefore, another disaster occurs in the near future. So that's what I would call the cycle of disaster. So all this so far are the conceptual framework I have laid out for my research. So from now on, I'm going to walk you through my research by using different studies to illustrate these three components that constitute my research. First, let's look at hazards. So in a recent paper, in a recent study, my PhD students and I have used, along with some other co-authors, have used two algorithms to map flood susceptibility in the city of New Orleans. And this slide displays the methodological flow charts, methodological flow work. And the primary data is remotely sensed data. And based on the remotely sensed data, we developed one flood inventory map and 9 flood conditioning factors. So the flood inventory map is developed, generated by images pre and post, prior to and post Hurricane Ida that struck coastal Louisiana in 2021. And we randomly selected 200 points with 100 long flood points and 100 flood points. And 70% of those points are used for training, whereas 30% of them are used for testing. On the right side, it shows 9 conditioning factors, and those conditioning factors are categorized into, classified into 3 categories: climatic and hydrological, anthropogenic, topographic. So here is the flood inventory map. As I briefly introduced earlier, we randomly selected 200 points across the city of New Orleans, with the red dots representing non-flood points and red dots representing flood points, green dots representing non-flood points. And here are the 9 conditioning factors. These conditioning factors include elevation, slope, aspect, precipitation, land cover, land use, normalized difference vegetation index, drainage density, topographic wetness index, and soil texture. The first algorithm, the first methodology we used is called frequency ratio model. Frequency ratio model is a traditional method that it has been widely applied for flood susceptibility mapping. So as you can see, the core of this method consists of only two equations. The equation on here and the second equation listed here. Because of this audience, I don't need to go too far to explain these 2 equations. I would encourage you to read this paper. I will be happy to share this manuscript with you once it's published. And the second method we used is random forest. And for this audience who's very highly technical, I don't need to go too much detail to explain random forest. And we all know that random forest is based on bootstrap sample, and each sample is developed by splitting data based on the best split with less impurity. And at the end, the majority votes will be selected as the predictor. So according to Random Forest, the biggest contributing factor among all 9 conditioning factors is elevation in the city of New Orleans. Elevation is the #1 contributing factor to flood susceptibility. What follows is precipitation, and the third primary factor is normalized difference vegetation index. And comparing frequency ratio model with the Random Forest, it is revealed that although these 2 methods have shown some common pattern, spatial pattern, they do have some differences. So for instance, I shall point out the very low classification, while frequency ratio model tells us only 18%, 18.52% of New Orleans is classified as very low flood susceptibility. Random Forest shows that, as a matter of fact, 1/3 of the area can be classified as very low. Another class that shows high discrepancy, big differences between these methods is the high category. So while frequency ratio model shows that 17% of the area has high flood susceptibility, Random Forest shows only 10%. So here are the 2 maps. On the left side is the map generated by frequency ratio model. On the right side is the map generated by Random Forest. So overall, comparing both side by side, the overall pattern is that the eastern portion of New Orleans have high flood susceptibility, whereas the western portion have low susceptibility, although the frequency ratio model reveals a larger area that's classified as very low flood susceptibility. And we also did some performance detection. According to ROC, AUC, Random Forest has shown better accuracy, higher accuracy with 0.83, whereas frequency ratio model shows lower accuracy with 0.72. Okay, before I move on to the next major components in my research, I would like to leave these 2 maps with you. Something to think about, something to consider for the future research. Okay, so there are 2 maps shown on this screen. On the left is the flood susceptibility map generated by Random Forest. The map on the right was generated by an online survey that was conducted back in 2021. If you compare these 2 maps, it's very clear these 2 maps are showing major discrepancies. Specifically, whereas on the right, there are areas that's classified as red, has been perceived as with very high flood risk. On the left side, it shows it actually has very low flood susceptibility. So I'm going to leave this question to you. What makes these 2 maps so different? In other words, what causes the public risk perception of flooding? So in order to answer this question, I'm going to propose this. Maybe flood susceptibility, exposure to flood hazard itself is not enough to measure overall flood risk. What's lacking here is the social component, and more specifically, is social vulnerability. So that leads us to the second major component in my research, vulnerability. Just to illustrate why studying social vulnerability, especially at an aggregate level across space, is so important. So we published this paper sometime last year. It was recently published in the journal Findings. Back in 2017, after Hurricane Harvey a large area of Houston was flooded, and the local emergency management was overwhelmed with a lot of requests for rescue. The organization Red Cross posted a website asking people who needed a rescue to pinpoint their location on a online map, internet map on the web, on the website. So that's how we collected this unique data set. And we collected the data, we collected 76,000 requests across Houston metropolitan area, including the surrounding counties. And you can see there are some demographic characteristics associated with this sample. Age, including adults, elderly, and children. There are also specific reasons why they requested rescues. Here is the spatial distribution of the requests rate. So the basic unit is a zip code. We calculated the rescue rate as number of people divided by the total population in that zip code. So this is how the map is based, what the map is based on. And among all the requests, we did a word cloud. And as you can see, water is a major issue. People were flooded, inundated, and they needed help. And other highly frequently mentioned words are old, help, please, rescue, family, trapped. So this is a word cloud generated based on the data we collected. And I'm going to share some of the major findings based on the data analysis. As expected, neighborhoods with a higher percentage of young children and people who live in poverty tend to have higher concentration of people who requested a rescue when controlling for the effects of all the other variables. So we know that for people, for researchers who have done research on social vulnerability, we should be familiar with how social vulnerability index is constructed. Oftentimes, this list of variables include percentage of children, percentage of people who are old, over 65 years old, and people who live in poverty. So surprise, surprise here. Another finding, major finding we have made based on the data analysis is percentage of people who speak limited English is negatively correlated with the rescue requests, indicating that not being able to speak English effectively poses challenges to people seeking rescues. We know that in Houston area, there is a big proportion of the population who are Hispanic, and many of them do not speak English as first language. So that language limitation poses as a major threat in the event of an emergency. So all these findings, these findings from this study tell us that social vulnerability is a critical component that can influence the outcome of disaster. So it's critical for researchers to bring the social dimension into the construction of overall resilience assessment. So with that in mind, I conducted several studies. So I'm going to present a couple of them here. So for instance, for this one that's currently under review, we looked at the spatial temporal patterns of community vulnerability in Mobile Bay, located in coastal Alabama from 2000 to 2020. Here is the study area. So once again, this is the methodology of flow chart, and our data come from two major sources. One comes from census data, the other comes from the National Land Cover data set. And all the data cover 2 decades from approximately from 2000 to 2020. And we conducted social vulnerability, we constructed a social vulnerability for each specific year, 2000, 2010, and 2020. On the other side, we did a land cover and land use classification, reclassification, and also in 2001, 2011, and 2019. And at the end, we made these two series of maps. Okay, here we go. Here's the first series of maps showing social vulnerability, the changing patterns of social vulnerability in Mobile Bay from 2000 to 2020. Just examining by eyeball, we can tell that the area with the heightened social vulnerability has expanded in the city, in the Mobile City area over time, over the 20 years, period of 20 years. To validate our observation, we did a hotspot analysis and cluster analysis, and both analysis validated our observation. Over the period of 20 years, social vulnerability has expanded beyond the limits of Mobile Bay City. And in addition to social vulnerability index construction, we also looked at the land use and land cover. And there are some changes, and mostly the results inform us that urban land, barren land, have increased in area, whereas forest land and grassland have decreased, although not that much. Okay, in another published paper, we used bivariate mapping, trying to connect the social vulnerability with exposure to physical hazards, specifically hurricane, wind hazard, storm surge, and flood hazard. And this paper was published in Disasters in 2020. And here I'm going to just show two maps to illustrate the outcome of this bivariate mapping, overlaying social vulnerability with exposure to hurricane wind hazard. And here's another map showing social vulnerability overlaid with exposure to storm surge across the US Gulf Coast. So we have talked about the importance of measuring exposure to hazards. And also it's important to measure social vulnerability. And in the last example, I talked about using bivariate mapping to display areas that have shown high level of both the social vulnerability and a high level of exposure to physical natural hazards. But is there any other methods for us to use to combine these two types of geographic information? So I'm going to propose that we could just use exposure to hazards multiplies social vulnerability that give rise to risk. In this particular case, I'm going to use the study on measuring assessing flood risk to illustrate this formula, this framework. So in this paper, that's still in preparation. We did use the formula I just laid out. On the left side is the flood susceptibility map we made for Harris County. And flood susceptibility, we used a flood inventory map generated by images pre and after post Hurricane Harvey in 2017. And this time we considered 12 flood conditioning factors. So in the earlier example I gave in the city of New Orleans, we only considered 9. But for this study, we are going to include 12 conditioning factors. So the final outcome is the map on the left, the flood susceptibility map. On the right side is a social vulnerability map. Once again, we use the very traditional methodology, PCA, principal component analysis, to reduce the data dimension based on census data. So the map is the final results of social vulnerability analysis. After that, we use the formula exposure to flood hazard times social vulnerability. We get this map, flood risk zones. So this is the preliminary result, and we are still working on the manuscript development at this point. Okay, so so far I have talked hazards, how to measure hazards, I used a specific example of mapping flood susceptibility in New Orleans and Harris County to illustrate the procedure to make flood susceptibility map. And I have also discussed why it is important to integrate social dimension into the whole construction of resilience assessment indicator index. Now I'm going to move on to the research area I'm most focused on over the past, I've been mostly focused on over the past 10 years, risk decision making. To date, I have most of my publications are focused on risk decision making. So in the paper that was published in 2017 in the journal Water Research, we examined what are the factors driving coastal residents to purchase flood insurance voluntarily, which means they purchase flood insurance when they are not required to do so. So one of the major findings we made is that FEMA's flood maps, FEMA stands for the Federal Emergency Management Agency, which is tasked in charge of flood management at the federal level in the United States. So one of the major findings we made through this study is that FEMA's flood maps have been effective in conveying local flood risks to coastal residents and correspondingly influencing their decisions to voluntarily seek flood insurance in the US Gulf Coast region, even when they are not required to do so. So what does that imply? It implies that FEMA's flood maps can serve as a powerful risk communication tool. So this is the major finding we made in that paper. And I later on drew a lot of inspiration from that finding. So more recently, in 2019, we published another paper related to flood insurance purchase behavior and overall flood mitigation measures. Once again, we made a similar finding. The flood risk informed by FEMA's flood maps not only provides the compulsory basis for flood insurance purchase, but also determines individuals' overall support for flood mitigation. So this has a fundamental policy implication. The fundamental policy implication is flood maps are have become such a powerful risk communication tool. Any inaccuracy on that map can immensely mislead individuals' overall risk mitigation decisions. So it's very important to make sure of the accuracy of FEMA's flood maps. So speaking of a flood, how powerful FEMA's flood maps have become as a risk communication tool, we wanted to test it out in a natural experiment. I don't know how many of you are familiar with this term, natural experiment. Natural experiment rose to fame a few years ago when 3 economists won Nobel Prize in economics for their contribution to causal inference. In real life, in real world, oftentimes researchers are constrained and limited by certain considerations, like ethical considerations. For instance, we cannot randomly assign people to smoking group and non-smoking group just to test whether smoking is harmful to your health. Or in this case, we cannot randomly assign people to living in a flood zone or living outside the flood zone. Similarly, for ethical consideration. So instead of the lab experiment, most researchers and scientists are familiar with, an alternative is natural experiments. So a perfect natural experiment arose in the event of Hurricane Harvey. Once again, I'm gonna take you back to Hurricane Harvey, the unique data set we collected from the Red Cross website, those people who requested rescues across the region. So here is a map showing the rescue rates in the Houston area in 2017 after Harvey, immediately after Harvey. And in this experimental natural experiments, we used a method called regression discontinuity. Basically, we wanted to see people who live within flood zone and people who live outside the flood zone, especially for those who live in the proximity of the border of the boundary of flood zone. They are similar, except one group lives inside the flood zone and the other group live outside the flood zone. We want to test which group tends to have higher rescue requests. Whichever group has higher rescue requests, it indicates that areas were at higher flooding risk. So I hope I make sense. I hope if you have any question, I'm happy to answer any question you might have during the Q&A session. So that's the design, regression discontinuity design. So we did find some gap. So for instance, people who live outside the flood zone, just in the proximity of the boundary outside the flood zone, the rescue rates in these neighborhoods are much higher compared to the neighborhoods who are immediately out inside the flood zone in the proximity of the boundary, flood zone boundary. So here is the gap. And what's more is that neighborhoods with a higher percentage of flood zone, the gap is larger. So this goes back to the finding I just shared earlier. Flood zone, the flood designation made by FEMA not only provides a compulsory basis on which people should buy flood insurance, but also serve as risk communication tool. Okay, lastly, I want to leave enough time for Q&A, question and discussion. So lastly, I'm going to briefly discuss a recently accepted paper in the journal Applied Geography. And in this paper, we use the participatory GIS to measure accessibility of people with movement-related disabilities during earthquake evacuation. And the lead author is my former graduate student, and he did his master thesis on this topic. And overwhelmingly, the literature on accessibility is mostly focused on objective data, objective indicators, assuming every person has equal capacity to access this transportation network in the event of an emergency. In this paper, we took this assumption on its head because people do have different capacities. For instance, people with the movement disabilities are limited, constrained by their physical movement, especially during the event of an emergency. Their movements are very constrained. The impediment, the barrier they are faced with are much higher compared to the general public, the general population. So with that in mind, we use the participatory GIS combined with the physical survey to measure accessibility for this particular group of people in the city of Dhaka, Bangladesh, a developing country with rapid, careless urbanization, and most people are at risk. And especially those people with disabilities are at even higher risk. So this is the framework, methodological framework. We use the participatory GIS. Basically, we ask first we transfer the GIS shapefile to Google Earth, and we zoom in to go to Google Street View and ask each respondent to rank the impediments, how accessible the roads is to them personally. And after we gather the data, we use the average, and then we applied that score to a formula called link to node ratio to get the overall accessibility index to the road network. Okay, with that, I'm going to stop here. So I'm happy to answer any questions. And if you don't have questions for now, I encourage you to contact me in the future.
Okay, thank Dr. Shao for her excellent and interesting talk. I think that's very interesting since we experience many natural hazards around us every day. And Dr. Shao used the remote sensing and GIS to conduct the risk decision making. So it's very valuable work. Now we go to the question and answer part. Please raise your question if you want to discuss with Dr. Shao. Anyone has any question?
I see one raise the hand.
Oh, yes, go ahead.
So please go ahead.
Yeah, you can unmute yourself to ask questions.
Hello, can you hear me?
Yeah.
Yes, we can hear you.
Yeah, hi everybody. My name is Victor Wang. I'm currently serving as a postdoctoral fellow at the Institute for Earth Computing, Human and Observing at Chapman University in Orange, California. So I have a question regarding the leverage of the indicator of the rescue request. So as a potential indicator for to what extent a community or population can be considered as a vulnerable or resilient to hazard impacts. So I think in your presentation, well, first of all, thank you so much, Dr. Shao, for this great presentation. So in this presentation, so in one case, you mentioned that the people, it seems that if people have a high percentage, high degree of this request for rescue, means that they are more kind of like have a higher tendency to impact or more vulnerable to a hazardous event. But in another case, when regarding the language issue, it seems that the less request of a rescue seems to be an indicator of a high vulnerability level. So I'm wondering, so how could we right? So how could we justify using this request for rescue as kind of like an indicator or maybe an output variable to train model, right? Regarding the vulnerability or resilience of the community, or is that a kind of like a middle optimal point at which that it means that it's the best point, and then the higher the request for rescue, the lower the vulnerability, and lower also the higher the vulnerability. So just a little bit, maybe Dr. Shao could clarify it a little bit. Thank you.
So thank you so much for your insightful question. I did put a lot of thoughts into the general construction of social vulnerability. I know that although there is a large body of work on social vulnerability, various social vulnerability indexes, there is a lack of validation of those indexes. Like you said, people might want to try to use different indicators as the outcome variable, trying to work backwards to identify what are the significant variables that can contribute to social vulnerability. And this variable, this data is quite unique in my opinion, but it's not comprehensive. Usually, if I were to validate social vulnerability index, I would use damage outcome fatality, for instance, in developing world, in developing countries, when a natural disaster occurs, the most impactful outcome is fatality, maybe mortality. Whereas in developed countries, the most impactful outcome is economic damages. So both can be candidates as outcome variables we can use to work backwards, identify significant predictors among a long list of variables that are theoretically conducive to social vulnerability. But for this variable, we did not, for this particular data, we did not particularly use for validation. We just examined the spatial distribution of requests rates, and we made these findings that confirms what we have known along the way, that people who neighborhoods, I'm sorry, not people, neighborhoods with a higher percentage of young children and higher percentage of people who live in poverty tend to have higher rescue requests. Does that answer your question?
Yes, absolutely. Thank you, Dr. Shao.
Yeah, if you were to use a data trying to model social vulnerability, you might want to consider more comprehensive indicators. This is quite limited in some sense. You might want to consider damage amounts, economic damage amounts, or fatality, the number of deaths, the distribution of spatial distribution of number of deaths across this area.
Yeah, I totally agree. I actually have some published papers with the leverage of the casualties, fatalities, injuries, and economic losses and damages as the output variables, to calibrate those quantitative models for social vulnerability and also community vulnerability in general. So I totally agree with what you've just said. Thank you so much.
So there is a question in the chat box. So this is from Shao from University of Arkansas. Well, thank you. So for your formula that involves the multiplication of flood exposure and social vulnerability, did you standardize them before the multiplication? If so, how did you standardize them? Is there any specific reason for you to consider multiplying them instead of adding them together? Thank you so much for these thoughtful, serious questions. Yes, we did standardize them. For the social vulnerability, we first normalized each variable by using z-score, and then we use the additive scale to create the social vulnerability index. For flood susceptibility, we basically adopted a very straightforward, a very simple framework, 0 to 1. 0 to 1 scale, and we did the same with the final social vulnerability index before we multiplying these two components together. Is there a specific reason for you to consider multiplying? The specific reason is that according to IPCC and a long line of research, the standard formula of calculating, estimating, assessing disaster risk is disaster risk equals hazard multiplies exposure to hazard multiplies vulnerability. So that's the reason behind this formula. And we argue that the flood susceptibility map we made, the procedure we used to produce the flood susceptibility map already considers both flood hazard, the conditioning factor, and also the exposure, because we use the flood inventory map to generate, to validate this flood susceptibility map. Does that answer your question?
I see that 这个 Dr. Huang has answered. Thank you for answering them. I think he is very satisfied with your answer, Dr. Shao. There is another question. Can you see that, Dr. Shao?
So this question is also related to what Dr. Huang asked earlier. The flood risk can be calculated by exposure times vulnerability. Okay, hold on. Let me move this. I see your equation for calculating how do you consider hazard as a component. So as I explained earlier, our flood susceptibility is the outcome. The flood susceptibility map is an outcome of the flood conditioning factor and the exposure to flood. So we did use the images generated immediately pre and post a hurricane-induced flooding event to validate those, to select, work backwards, to select those predictors. So it already contains both components, the exposure and hazard. I hope I have explained this well.
Okay, thank you. Does anyone have any other questions?
I have a question. Hi, Dr. Shao. Thank you for your great lecture. And I'm a PhD student from Auburn University. I have a question about your first case study. And you mentioned you selected some conditioning factors like the precipitation and DVI and something like that. And I'm was curious about, have you selected other factors like soil moisture or even evapotranspiration on the flooding?
We did not consider those for the first case study, but we did consider 3 additional factors for the second one, for the one that was conducted in Harris County. I don't recall off the top of my head what are those 3 particular additional factors we included in the flood susceptibility mapping for the Harris County, but I remember one of them is distance to river, because we changed the geographic area from New Orleans to Harris County, and there are rivers running through the city, running through the county. So it's very relevant. I don't remember the other 2 conditioning factors, but for the first study, we did not, because here are the 9 conditioning factors we considered. What were the ones you asked? Evaporation and the soil moisture?
Yes.
Yeah, we included a soil texture, and in New Orleans, drainage density and precipitation are highly relevant, and because the city has experienced multiple heavy rainfall events over the past several decades, and we did some pre-screening. It's geographically specific because it's in New Orleans. We selected those factors that tend to be most prominent contributing to flood in New Orleans.
Okay, thank you.
I can get back to you with the 3 additional factors we included in the case study of the Harris County later. You're at Auburn, right?
Yes.
Yeah, you please email me. I will get back to you.
Okay, thank you so much.
Okay, thank you very much. And does anyone have any questions? You can unmute yourself directly and raise your question.
Looks like
Hi, Dr. Shao. This is Yi Chang from University of South Florida. I really enjoyed your presentation, and yeah, thank you very much. I have two questions. First is about your research on flood susceptibility maps. Well, since I'm living also in a coastal area that has a flooding induced by hurricanes and storm surge, I wonder how transferable your models are. For example, in this case, it's being applied in New Orleans. We all know New Orleans, in many areas in New Orleans, is already under the sea level. So the levees and dams play an important role in preventing flood in New Orleans. I wonder, I think my question is, do you think your model can be applied to areas where other types of flooding is more prevalent? For example, we know flooding could be fluvial or fluvial. For example, whether your models are applicable in inland area where the fluvial flood is more prevalent. And my second question is, thanks for sharing so many publications, and I realize that not only you are productive, but also your students are very productive. If you can share some of your experience, how you mentor your students to create a publication, that would be great for, for our faculty audience. Those are my two questions.
Well, Dr. Chang, thank you for your generous comments, and thank you for your great questions. So flood susceptibility mapping is not a brand new topic. It's not groundbreaking work we are doing. There's a long line of research on flood susceptibility mapping. As I pointed out in my first study, the traditional method is called frequency ratio because it's very straightforward. You just use these two formula equations. You can classify by using, of course, based on the flood inventory map. And on top of that, we can add several flood conditioning factors, whether it's 9 in my first study or 12 in my second flood susceptibility mapping study. So flood susceptibility mapping itself is nothing new. And you asked whether the model can be applied. I think it's just like social vulnerability index. Social vulnerability index is nothing, it's not a brand new topic. Yet, still many people are still making a lot of effort creating social vulnerability index across different geographic area at different geographic levels, because it's very place-based. Like I explained earlier to one of the questions, why when we changed from New Orleans to Harris County, we expanded the list of conditioning factors because we changed the geographic area. In New Orleans, the major influence is the location. It's a bowl shape and largely located below sea level. But in Harris County, another contributing factor is the river that runs through the Harris County, the county of the county. So when we change place, we have to think about these geographically specific factors when we select these conditioning factors, just like when we create social vulnerability indicators. Although there is a list of variables that are commonly recognized, acknowledged as factors contributing to social vulnerability, that doesn't mean we should use exactly the same list every time. And the flood inventory map is largely used as validation. Basically, just like the earlier when I discussed social vulnerability, how we can validate social vulnerability, we can use some outcome variable to work backwards to identify significant variables and then use those significant variables. Maybe we can use some advanced methodology. We can also use the information derived from those methodology to weigh each particular significant variable when we construct the final social vulnerability index. Exactly the same logic applies here when we make flood susceptibility map. We use the flood inventory map because those areas are either flooded or not flooded, and they are real outcomes. We can use those as outcome variable to work backwards to select which conditioning factors make what kind of contribution to the flood susceptibility. Does that answer your first question?
Yes, yes, I get it. So basically, in different areas, you choose different conditional factors, right?
Yes, but more or less, you contain most of those factors should remain the same. For instance, on this slide, these 9 conditioning factors, I would argue that they should apply to everywhere. These are fundamental flood conditioning factors, whether we're talking about precipitation, topographic wetness index, normalized difference vegetation index, land cover, land use, and elevation, slope, aspect, drainage density, soil texture. Those are the fundamental flood conditioning factors. On top of those fundamental factors, we can adapt, we can add more or less to this list. Yeah, so that's my answer to your first insightful question. For your second question, I'm still learning along the way. You might see my students, sometimes you get lucky. Sometimes the students you recruited happen to be highly motivated. They don't need so much motivation, so much pressures from you. They can work on their own, and you enjoy every discussion with them. Sometimes, you might not be so lucky, throughout our entire career. I'm certain that we can meet either highly motivated students and the other cases. So, but in general, I always take a very positive way when I communicate with them. I always encourage them. I always try to identify their strengths and emphasize their strength to them. And I praise them a lot. I give them a lot of encouragement. So that's my communication strategy when I mentor my students. I also I'm very hands-on. Like I'm sure everybody has the same experience. Each student has their own strengths and weaknesses. Some students tend to be very skilled in data analysis, in those computation, very skilled, very technical. Some other students are very good at writing. We are academics, developing manuscripts, writing skills are also highly appreciated. So you have to balance. When you see students display strength in writing, you might want to spend more time with them, encouraging them to further develop their technical skills. When you work with the students with high level of technical skills, but still need a lot of improvement on their writing, you might need to spend more time with them and writing with them, walking them through the manuscript development process. So that's my overall strategy. Of course, each individual is different, and we need to always identify their strength and constantly encourage them.
Okay, so there is another question from Heng in the chatting box, and also I think the time has almost run out. So can you give a quick answer for this question?
Oh, okay. Yeah, I'm still reading the question.
Okay,
Index validation is challenging. Regarding index validation for either vulnerability or resilience, other disaster damage data, do you have any thoughts on what empirical data and what methods can also be used to validate the index damage data? Is good option to reflect response disparity, but recovery is also another important component in the concept of resilience. I agree. Damage may not reflect recovery, since some communities may suffer higher damages but have quicker recovery. Excellent question. These questions are very insightful, and I would say that the literature is still in development. And as Dr. Chang shared with us last week, there is still no consensus on how to define resilience, not to mention how to measure resilience. There are many ways. And from my own research experience, I'm mostly familiar with the social network, social capital. And if it were to me, in terms of how to measure resilience, I would consider social capital. Social capital basically means how integrated, how cohesive a community is with each other. And many empirical research has shown to us that communities that displays high level of social capital recover better and faster. And that's one area I'm planning to explore in my future research. But excellent question. Yes, you are right, pointing out damages does not reflect the recovery. The damages only reflects vulnerability and exposure to hazards, risk. Recovery is part of resilience. How we recover from a disaster is a different story. And I would argue that risk mitigation, risk decision making is also a critical component. But what kind of factors shape risk decision making? It's a very complicated topic waiting for researchers to explore more in the future.
Okay, thank Dr. Shao. And I see all the audience are really enjoying this talk. I guess many of them still have some questions or something to discuss with Dr. Shao. But we have to finish today's talk since it's a 1 hour webinar. Now, thank Dr. Shao for your excellent talk, and thank Dr. Qiusheng Wu for your careful coordination, and thank all the audiences for your time and participation. We still have a couple of talks in the next weeks. So we are looking forward to see you in the next talks. Is there any notice from Dr. Qiusheng Wu?
No, thank you very much, Dr. Shao, for the insightful presentation, and Dr. Lee for hosting it. And thank you everyone for attending. We will see you next week. Take care. Bye-bye.
Thank you for your attention. Have a good
Thank
evening.
you. Bye-bye.